Good evening. Welcome again. So this is week number 4. Next week will be your term test 1. Okay, term test 1 will be until here, depending on where we finish. So first of all, I have to apologize. I could not post any tutorial, 1-hour tutorial, because I have a swollen eye. My right eye was infection, so my right eye was very small. I could not see at all. Okay, so I do apologize. But you can also, if you're not clear about sharing stress, I think the videos are, if you don't, at certain aspect you don't understand, you should watch the video again. How often do y'all watch the video? Do y'all watch it or no? Anyone? Yeah, do watch it, okay? So is partitioning the videos every 15 minutes help or no?
Yeah, that's good.
Okay, I'll keep on doing that, okay? Right. So today we're going to complete the example that we started last week. And then we are going to go into longitudinal shear or beam section. This is very useful for building a deck. How many of you are thinking of building a deck? Anyone?
They don't last. Get a patio.
I did it
Okay.
before.
Yeah, I'm
Class
going
gives
to
us too much homework, so we don't have time.
yeah. So I'm going to teach you. I've been doing a lot of consulting about calculating stresses on a deck for landscaping company, and I'm going to show you what I did to do the analysis, and it's not difficult at all. It's pretty straightforward. So it's longitudinal shear. So what this longitudinal shear will help you is determine how many nails to nail down, okay, on your frame. How many nails? I know the standard is 6 feet or 6 inch. I couldn't remember now. But why? Okay. So we are going to do that. Okay. Then we are going to shearing stress in thin wall. Okay. These two topics I explained, formula did not change. Okay. Where shear flow is VQ over I. Shear stress is also VQ over IT. What's more interesting is that the rules, the 4 rules that I state for you guys, still apply. So we are not going to learn anything unique today, but you're going to watch how is it applied to different circumstances. Okay, how is it going to be applied? Right. So last week, what we did, we had a long example. Right, we have a cross section like what you see. We calculate the flange section. Right, so just to recall, this is what we call the flange, right? And then we come up with an expression for the shear stress for the flange. So this equation will only work from 0.05 y up to 0.035. And the centroid, okay, the centroid over here, right, where I'm highlighting, the centroid is the datum. The location of the datum is at the centroid, okay? Then we go for the top web section. Another thing that I highlight a lot of times, regardless of where you analyze the structure, Vy and Izz are always what? Constant, right? So one of you asked earlier, what if now is going to be Vz? If that's the case, Vz and Yy, Iyy are always what? Constant, okay? So from here, we work out an expression that the top web section. So for the top web section, right, we come up with an expression that this is the relationship. Okay, there's a relationship. Now this is the shear stress distribution. So I remember a student asked, isn't shear stress equal to force divided by area? True. Shear stress is also equal to force divided by area, but that is the average. This is a what? Distribution. Why is it a distribution? Because it's going to be a function of what? It's a function of y. Okay, it's a function of y. That's why it is different from what you usually do or what you normally do. Then how do we know it's correct? So we analyze the structure from the bottom web section. So what do I mean by bottom web section? So this is the bottom web section where I'm going to, so this is the bottom web section. Okay. So we analyze from the bottom web section. The datum is still at the neutral axis, but the analysis starts from Y max. Okay, so the bottom part at this distance over here, right? This is your what? Y max. And some of you say, Eugene, is below and above the centroid, it should be minus. You're absolutely right. But it does not really matter. Why? Because at the end of the day, the expression over here is y squared. So whether is it positive y or negative y does not really matter at all. Okay, does not matter at all. So from here, okay, at the bottom section, we derive another expression. And then we had this relationship. Okay, so now I'm going to sketch. I mean, I did this briefly. So I'm going to sketch the distribution now. Okay, I'm going to sketch. So far, anyone, any question, or we're okay? We're okay? Right. So this is what we have. Okay, so I'm going to, so this is the centroid where I'm going to draw. So I'm going to sketch. This is our centroid. Okay, so again, this is just a sketch, right? So over here, this is our centroid, position of centroid. And then we are going to draw, oops, and we're going to draw our shear stress. So this is our shear. And then we have our y. Okay, so if we were to draw transformation, this is y, this is z, and this is our rotation in the x. So we know at this point down here, this is 0.035, right? And then at this point down here, this is 0.065. Okay, so I'm going to label this. This is our flange. And over here, this is our web. So from here, we will have a curve. Okay, so I'm going to highlight that this is where the intersection of the flange and the web occur. So we're going to have a curve down here that look this way. And this curve over here, right, has the expression. This curve over here has the expression of this equation over here. Okay, so it has the expression, right? Okay, it's doing something funny, but let's see whether it will move. Right. Okay. And then because of the change in your what? Of your thickness, because of change of thickness, you see a step, right? Because the thickness changes. Okay, so you have the curve doing this. And then from here, it's going to do this. Okay. And this position over here, this is your location of tau max. And tau max is equal to 32.705 times 10 to the power 6 Pascal. And from here to here, this section over here, right, for the entire web, we realize that the shear stress distribution function is equal to shear xy is equal to 32.705 times 10 to the power 6 minus by 7.7409 times 10 to the power 9 y squared. Okay. So that's what those equations, the equations of distribution we're drawing. That's why you can see. So this is our top of the web and the bottom of the web. The shear stress distribution equation, right? As you can see over here, for the bottom of the web, it's exactly the same as the what? As the top of the web. Okay. Is that clear? Right? Is that y'all can see that? Yes or no? Right?
Yep.
Okay. Now, what I'm going to do now is we are going to calculate. Okay, we're going to calculate. Right? We're going to calculate. Okay, we're going to calculate. Okay, we're going to calculate the shearing stress at point A. Okay, we're going to calculate the shearing stress at point A. So the shearing stress at point A is equal to Vy over Izz Qz at point A, right? Or Qz for A. And then we have our what? We have our thickness. Okay. So from here we realize that the thickness, there are two thicknesses you can use. The thickness can be equal to, so if you look at point A, all right, you realize that this is in the intersection. The thickness will be equal to 0, can be equal to 0.16 meter, or can be equal to what? 0.04 meter. So we usually choose the smaller t, right? Why the smaller t? Such that the tau will be what? The shear stress will be
Greater.
will be higher, will be greater, right? So if we go back to our Vy, so I'm trying to get my notes to, so our Vy, can someone tell me what's our Vy value, please? Vy is it equal to is equal to what? Is equal to 90. Okay, 90 times 10 to the power 3. And then Izz will be equal, so if we look at Izz is 5.8133. Okay, 5 times 10 to the power minus 6 meter to about 4. So next we're going to calculate the Qz, okay, at point A. So it's equal to area y bar, right? So the area, we're going to take the entire flange, right? So A is equal to the width. So I like to do width multiplied by depth multiplied by y bar. So the width, we know that is 0.16. The depth is equal to 0.020. And then the y bar, so the y bar, so we know that the distance, okay, I'm going to, the distance from here to here, we know that this is 10 millimeters. And then we are aware that our centroid, right, our centroid, this distance over here is 35 millimeters. So what we want to find out is this distance from here to here. This is our y bar. Okay. So from there, our y bar will be equal to 0.035 minus by 0.01. Okay. So this will be equal to 0. Times by 0.02 times by 0.16 is equal to 80 times 10 to the power minus 6 meter cube. Okay. So therefore,